Hi, I'm Chem's best friend. If you need chemistry help, the information how to contact me is on the bottom of your screen. So hi, welcome back. In this series of videos, we're going to learn more about atoms, the structure of an atom, and most importantly, where are the electrons in an atom? That's a very, very important question. Remember, why do we care about where are electrons? Well, chemical reactions are all driven by electrons. Atoms want to share electrons, exchange electrons, transfer electrons, all to become, more stable. So what am I talking about? Let's try to find out. Okay, let's go to my screen, and we have to go for a little history lesson. So we talk about models of an atoms. So in 1803, John Dalton proposes his first model of an atom, Dalton's atomic theory, and he says that an atom is this indivisible, indestructible sphere. He actually used wooden balls to show what an atom looks like. So they are these little tiny solid spheres. Then in 1904, J.J. Thomson discovers electrons. He does this cathode ray tube experiment, and he discovers electrons. So in 1904, we have a first subatomic particle. So now we have something smaller than an atom. And remember, what did John Dalton say? That atoms are the smallest unit. After J.J. Thomson discovers electrons, we have to have a new model of an atom, and we have it what's called a plum pudding model. So we have this smear of positive charge, and the negatively charged particles, electrons, are distributed in this smear of positive charge. Then in 1911, Rutherford does his famous gold foil experiment. And he shines some alpha particles, he shoots alpha particles through gold foil, and around 2% deflect, 0.01% shoot back right at him, and he says, what's going on? It takes him a year to figure this out, and he comes up with a new model of an atom called the nuclear model. He says there is a nucleus that contains all the mass of an atom, incredibly dense. The positive charge is now in the nucleus, and electrons are flying around the nucleus. The nucleus volume is tiny compared to the size of an atom. If you have a big football stadium with all the spectators and fit 60,000 people in this stadium, the nucleus is a little M&M on a 50-yard line. So that is the size comparison of nucleus of an atom. It is tiny. So that means most of an atom is empty space. So the electrons are flying in this empty space. So where are the electrons? What are they doing? Rutherford did not answer that. So here is just our history of atoms. Here are different theories. So here we have John Dalton first, then we have J.J. Thomson, plum pudding model, Rutherford nuclear model, and now we're going in the next series of videos, go to these next two models, the planetary model and the quantum model. So where are the electrons? That is the big question. Where are the electrons? Let's write this. So where are the electrons? And then we also have other questions. So why does each element emit unique emission spectra? So here is different emission spectra. Here is hydrogen atom, here is neon, here is mercury. So we have every element has its own unique fingerprint by the light emission spectra. Why? What's going on? Why do objects change color when they are hot, especially metals? If you look at this iron rod, you know for sure that this side is much hotter than this side. If I asked you to grab it, you will hold it probably around here. Now you know that this yellow color is hotter than this red color right here, which is hotter than this, gray-black color. Why? How can we do that? How can we tell the temperature from the color? Also, why does the periodic table work? So periodic table was developed in 1869 by Dmitry Mendeleev in Russia. And remember, we're talking about 1910, 1911, the nuclear model of an atom. This is about 40 years. But yet, we still don't understand why this periodic table works. So all of these questions we will try to answer, because all of them lead back to the most important question that we're trying to answer. Where are the electrons? What are they doing? So, before we answer all of these questions, we must first talk about light. Remember, we're still trying to answer why does each element emit its own unique light emission spectra. So what is light? Well, light is part of an electromagnetic spectrum. You have to memorize this electromagnetic spectrum, and here it is. I highlighted this. So we have well, let's start with something that we know. We know visible. Visible light is right here. And visible light is colors of a rainbow. And we have one end of a rainbow is red and one end is violet. So next to red, what type of radiation has the word red in it? Infrared. Infrared is right here. So next to visible light is infrared. Infrared is night vision goggles use infrared. That's your, like, it senses heat. Infrared radiation. And James Webb telescope actually uses infrared light to see the stars, which is really incredible. Then we have microwaves and radio waves on this side of the visible light. So, and then the one side of visible light is violet. What is another electromagnetic radiation that has the word violet in it? Well, ultraviolet. So on this side of visible light is ultraviolet. We have UV light, we have then X-rays, and we have gamma rays. And right here it gives you a little idea of how big these waves are. So radio waves are big. They can be kilometers or meters big. They are the size of buildings, of football fields. Somewhere between radio and microwave, we have human-size waves. Microwaves, I think of centimeters, right? Think of insects, centimeters. Infrared, we are going very, very small. We're talking a little bit about micrometers. When we have visible light, we're talking about nanometers, because this is between 400 and 750 nanometers. We have UV, which is smaller. X-rays are the size of angstroms. Here we have angstroms, which is the diameter of a small atom. And then we have gamma rays, much smaller even than the size of an atom. So this is beautiful here. You can have a look. This is, very, very short waves and getting much, much, much longer waves. Okay, let's go a little bit, one more picture. Here is one more. Here it's the same picture, only flipped a little bit on, like a mirror image. So again, we have visible light in the middle. Now look, visible light takes a very, very small chunk of the electromagnetic spectrum. I like this slide because it shows you actually the wavelength of visible light. And here you have violet, and next to violet you have UV light. Next to red you have infrared light, shows you. So visible light, ultraviolet, X-rays, gamma rays, visible light, infrared, microwave, radio. It shows you wavelength. Again, wavelength you can compare, but then on here it shows you a little bit at frequency. We will come back to this in a second. Okay, so all electromagnetic radiation travels at the same speed, which is then the speed of light. Speed of light is given by constant c, and here it is, 3.00 times 10 to the 8th meters per second. Some teachers or textbooks will say it's 2.998 times 10 to the 8th meters per second. They just go one more extra sig fig. I personally think 3.00 times 10 to the 8th meters per second is fine for chemistry classes and AP Chem, and it's a nicer number, so I'm just going to use this number. Let's talk about waves. So if you measure, how do we measure wavelength? So let's measure it from peak to peak. We call this wavelength, which will be the units of length, which the SI unit of length is meters. And it's we say that wavelength is lambda, put a symbol on it. So lambda, a Greek letter lambda, is wavelength. You can also measure it like from the valley to valley. You can measure it from going down to going down. You can measure it going up to going up. It will be the same wavelength. And then if you imagine here is you, and you're going to stand, and you're going to see how many of these waves come per unit time and knock you over at the beach, well, you will be measuring frequency. And frequency is, well, how many waves come per unit time. Usually we will say it's symbolized by Greek letter nu. So here it is, Greek letter nu. And it's then 1 wave per unit time. The SI unit of time is seconds. So we will say 1 over seconds. And it's also known as hertz or s to the negative 1. So we have wavelength frequency. We do not care about amplitude right now. Amplitude is an intensity. Brightness, we do not really care right now in chemistry class for that. So if we just look at the units, so speed of light is wavelength times frequency, lambda times nu. And let's double check, do the units make sense? So speed of light, meters per second, wavelength is meters, frequency 1 over second. If you multiply meters times 1 over second, you have to have meters per second. So always double check to make sure your units make sense. Units are your best friends. They really guide you along to make sure you're doing the problem correctly. All right, so we know about speed of light, wavelength, frequency, and then early 1900s, Albert Einstein does his famous experiment, and he discovers photoelectric effect. He actually gets his Nobel Prize for this experiment. He did not get a Nobel Prize for his theory of relativity, which is really interesting, but that's another story. So Albert Einstein comes up with photoelectric effect. What does he do? Well, he had a piece of metal surface, and he then shone light onto it, and he wants to remove electrons. And right here was actually a rod that sensed electrons when they were removed from a metal surface. And he says, he realizes that only light at a certain frequency can remove an electron from the metal surface. So it didn't matter how long he shone the light, and the intensity did not matter. This is not important. So time intensity was not important. Only frequency was important to remove an electron. He realizes that this then has to be little packets of energy to remove electrons. He calls these packets of energy quanta. He gets together with Max Planck. So Albert Einstein, here is our Albert Einstein and Max Planck, and they come up with this equation. Energy is directly proportional to frequency. And here is H is Planck's constant, and it's some constant you either have to memorize or your teacher might give it to you on equation sheet. So they realize that here is energy is directly proportional to frequency, right? So Albert Einstein recognized this as quanta of energy. And here's the big thing. So he makes a jump and says, wait a minute. If we have these packets of energy, this quanta of energy, that means light, which is energy. Light is a particle. And he calls that particles of light photons. And this is why he gets a Nobel Prize, because we always thought light is a wave. Remember, that's how we started our discussion. Light is a wave. It's part of the electromagnetic spectrum. And now Albert Einstein says light is a particle. What? Where would this lead us? All right, before we keep going with a story, I actually think we should learn how to solve these problems. How do you solve these problems with light, energy, wavelength, and frequency? So let's take a second to make sure you know how to solve these problems together, okay? Let's go. So here is a problem. Calculate the energy in joules of a photon of violet light that has a frequency of 7.42 times 10 to the 14th hertz. Is this energy greater or less than that of light of 655 nanometers wavelength? Explain. Let's Let's think about this. We actually have to do a problem, so we know that one light is, well, violet light. So I'm going to say, let's deal with violet light. I'm going to write it in violet. And this violet light, I'm going to say, is a short wavelength. Well, let's look quickly. Let's so here is our picture. We have violet light, and this means, look at the wavelengths, this is the short wavelength end. And then we have a light that's 655 nanometers. Oh, it's going to be right here. It's going to be red. So this is going to be a longer wavelength, right? So, so it's going to be longer wavelength, and it's going to be low frequency. Let's keep going with a problem. So this will be, and this is going to be our red light. And this will be our 655 nanometers. So this is longer, long wavelengths, right? And it's going to be low frequency. And this one will be short, but it will be high frequency. Right? And looking at this equation, remember what we said, energy is directly proportional to frequency. So if you have high frequency, you will have high energy. So we can actually answer the question right now without any math. And we recognize that which one will have higher energy? The violet light. Yes, so we know that the answer should say to us that this should have more energy. And this one should have less energy. So now let's do some math and make sure. All right. So our violet light has this frequency. Nu is 7.42 times 10 to the 14th per second. Yes. And we know the equation. E equals h nu. And we're going to plug in the numbers. So our energy equals Planck's constant, 6.626 times 10 to the negative 34 joule times seconds. Yes, times 7.42 times 10 to the 14th per second. Make sure your units cancel out, right? Seconds, then per seconds. So they will cancel out, and we will have units of joules. So this energy, you plug in the calculator, you should get 4.92 times 10 to the negative 19 joules per photon. This is joules per 1 photon. All right, now let's go here. Here we have nanometers, so we have lambda. If I can figure out frequency, I can then figure out energy, yes? So that makes sense? So I'm going to use my equation of speed of light equals lambda nu, yes? So if I can figure out my frequency by doing c over lambda. Now c is in meters per second. So that means I need to divide it by lambda that's in meters. But this here, it's 655 nanometers. So I have to change it to meters, right? So let's quickly do this here. Let's plug this in here. So if I have 655 nanometers times, we're going to do 1 meter is 10 to the 9th nanometers. This will be 6.55 times 10 to the negative 7 meters. That's my wavelength. So now I can quickly plug this in. So I have 3.00 times 10 to the 8th meters per second divided by 6.55 times 10 to the negative 7 meters. And if I do that, I'm going to get my frequency will be 4.58 times 10 to the 14th per second. Now, before we keep going, 1 second, let's do this. Look, here is my frequency right here of my violet light, and here is this frequency of a red light. And you can just compare these numbers, 7.42 times 10 to the 14th and 4.58 times 10 to the 14th. Energy is directly proportional to frequency. That means higher frequency, more energy, right? So right away, I'm comparing these numbers, and this tells me this is higher frequency. It will have more energy. But we can keep going to just make sure. Here's our frequency. And then again, we have E equals h nu. So we're going to plug this in. Planck's constant, 6.626 times 10 to the negative 34 joule times seconds times 4.58 times 10 to the 14th per second. And here this energy of this red light is 3.03 times 10 to the negative 19 joules per, this is per photon. Remember, Planck's constant is per photon. And here I can compare, let's compare these numbers. Here is this energy versus this energy. And you can see that violet light has more energy. Okay? Is this making sense how to solve these problems? Let's do a few more. So here we have laser compact disc player produces light with a wavelength of 780 nanometers. I would like to calculate energy in joules per photon and then in kilojoules per mole of photon. So here's something a tiny bit different, but similar. But I think what you can see what's different is I'm flowing in this. I would like to know in kilojoules per mole of photons. So are we ready? Okay, so same idea as before. We have wavelength. If I have wavelength, I can figure out frequency. If I can have frequency, I can figure out energy, right? All right, so I need to change my wavelength to meters because that's the SI unit. So let's do this. So if I have 780 nanometers times 1 meter, 10 to the 9th nanometers, I'm going to have 7.80 times 10 to the negative 7 meters. That's my wavelength, right? And then I have, well, C equals lambda nu. So I can figure out my frequency, C over lambda. So I have 3.00 times 10 to the 8th meters per second. Let's divide it by my wavelength. 7.80 times 10 to the negative 7 meters. And this tells me my frequency then is 3.85 times 10 to the 14th. And this is waves per second, yes? So per second or hertz. And then energy equals h nu, Planck's constant times frequency, which we will then do 6.626 times 10 to the negative 34 joule times seconds times 3.85 times 10 to the 14 per second. And then energy is, you plug this all in, 2.55 times 10 to the negative 19, and this is joules per photon. Now, here we go. So we did the first part. We want joules per photon. Here it is, joules per photon. Now we're going to go to kilojoules per mole of photons. So let me change color. Let's go with green to keep going, or maybe with blue. Okay, if this is joules per photon, so I'm going just to rewrite this. I have 2.55 times 10 to the negative 19 joules per photon. What's the definition of a mole? Well, has to be 6.022 times 10 to the 23 photons per 1 mole. Yes? Now, I already have, so my photons cancel out. I'm going to have moles, but this is joules per mole. But I want kilojoules per mole. So we will have times 1 kilojoule is 1000 joules. And I plug this in, and remember 3 sig figs, I'm going to have 153 kilojoules per mole of photons. There we go. How did we do? Is this making more sense? Okay, last problem. Are you ready? Last one. So here it says, the minimum energy necessary to remove an electron from an iron atom is 7.21 times 10 to the negative 19 joules. What is the maximum wavelength of light in nanometers that will show a photoelectric effect with iron? Okay, so do you notice what's the deal with this problem? Before, I gave you wavelength and I asked you for energy. Here, I'm giving you energy and I'm asking for wavelength. So can you do the same process going backwards? Let's do it. Well, we give an energy, right? So we have our energy, 7.21 times 10 to the negative 19 joules. And energy also, what's the equation for energy? Equals h nu. Well, if I have energy, I can figure out frequency. And if I have frequency, I can figure out wavelength. Yes? That's my plan. So, what's wavelength? I'm sorry, what's frequency? Frequency is energy over Planck's constant over h. Right? So, let's do this. So we have 7.21 times 10 to the negative 19 joules divided by Planck's constant, 6.626 times 10 to the negative 34 joule times seconds. And look at this. Joules cancel out, and I'm going to have 1 over second, yes, which is great. So if I plug this in, I'm going to have that my frequency is 1.09 times 10 to the 15 per second or hertz. And C equals, yes, speed of light equals wavelength times frequency. I know frequency, so what's my wavelength? So wavelength equals speed of light over frequency. So we will have 3.00 times 10 to the 8th meters per second divided by the frequency that I just found out, 1.09 times 10 to the 15 per second, right? So per second divided by per second will be 1, and I'm going to have meters, right? So I plug this in to my calculator, and I'm going to get 2.76 times 10 the negative 7 meters. But the question is asking me in nanometers. So I'm not done yet. I have to keep going. So I have 2.76 times 10 to negative 7 meters, yes, times, well, there is 10 to the 9th nanometers in 1 meter. So this will equal like 275, 76 nanometers. All right. So the question is, what part of electromagnetic spectrum is this? Well, do you remember? Visible light is between 400 and 750 nanometers. Let's quickly remind ourselves. It's right here. So we are at 275, 76. So we have to be right here on this end because we have to be less than 400. So we are in the UV region. Yes? So let's actually write that. So this many nanometers is not in a visible light, it's in the UV region. And that's it. So are you getting better at solving these problems using light, frequency, wavelength, and energy? But remember, we never even answered the problem. Where are electrons in an atom? It will take us few more videos to get to the answer. So I hope to see you next time, and thanks for watching.